moving from talking about oscillatory motion into talking about waves. So a wave is basically a natural phenomena that allows you to transfer energy from one place to another place. And there are different types of waves. So let's talk about those. First of all, there are all sorts of waves in nature. There's, light waves, and there's sound waves, and there's waves that are on a vibrating string. And what we're going to first focus on in this course are mechanical waves. Mechanical waves have to travel through a material, and that material is referred to as a medium. And there are two types of mechanical waves. One you're very familiar with, sound waves. Sound waves are called compression waves. And when the energy travels through the medium, as it travels, it causes the particles in the medium to vibrate back and forth parallel to the direction of wave motion. And as it vibrates those particles on the front end of the wave, the particles get compressed, and when the wave passes through that point, they get decompressed, right? So they're compressed to begin with, and then they're decompressed as the energy moves through that material from one point to another. Notice that the material isn't moving from one point to another. It's this invisible force that's moving through it that's causing those particles to vibrate back and forth. And we can model that motion like a simple harmonic oscillator. If we were to take one point and look at it move, you'll get compressed and then get decompressed. We could model it like a simple harmonic oscillator. That's why we start talking about SHM first. Sound is a great longitudinal or compression wave. Transverse waves you're also familiar with. If you've ever shaken a rope up and down, or played a piano, or watched somebody play a stringed instrument, whether it's a guitar or a cello or a violin, they all work the same way. You cause the string to vibrate, and it vibrates up and down. So the string is the medium, and it's vibrating perpendicular to the direction of wave propagation. So the wave is moving down through the string, and as it moves through it, it causes the string to move up and down, to vibrate up and down, kind of like a spring going back and forth. What's interesting about that is that the string itself is not moving from point A to point B, right? It's just vibrating up and down as if it's a string vibrating up and down. It doesn't move from, the energy is what goes from point A to point B. So all of the waves, whether it is a compression wave or whether it is a, something else, all of the waves, whether it's a compression wave or a transverse wave, whether it's a sound wave or a string vibrating up and down, have common properties. First of all, just like in simple harmonic motion, we talked about the amplitude. It's the height to the equilibrium point. So when the string is flat, or the sound wave is not, moving through the air, that's called equilibrium. The wavelength is the distance between two successive points. So it could be the distance between two troughs, or it could be the distance between two peaks, or it could be the distance from equilibrium where it's on the way up to the next point where it's on the way up. So it could be from here to here. That's a wavelength as well. It's measured in meters or centimeters. Period is a time for that one wave to occur. In seconds, frequency is how many waves per second pass a given time. And we know that frequency is inversely related to period, just like it was for simple harmonic oscillators. And the other thing is speed. Speed of the wave is equal to the wavelength, which is given by the Greek letter lambda times the frequency, or lambda over t. So if I want to know the speed of propagation, meters per second, I need to know the wavelength and the frequency, or the wavelength and the period. So let's just do a couple examples. So a piano string is vibrating with a frequency of 440 hertz. And it has a wavelength of 10 centimeters. Let's go ahead and change that to 0.10 meters. And if we want to know the speed, it's just lambda f, or 440 hertz times 0.10 meters, which is going to be equal to 4.40 meters per second. So just so you see how that works, a hertz is a 1 over a second, and you're multiplying by a meter, so you get meters per second. A wind gust creates ripples in the ocean that have a wavelength of 3.23 centimeters, or 0.0323 meters. And it has a propagation of 7.12 meters per second, and we want to know frequency. So V equals lambda F. F is going to be equal to V all over lambda, or 7.12 meters per second, and you need to make sure that you're dividing by the meters because the speed is in meters. This is what we mean by dimensional analysis, right? Understanding how the units work. So that's going to be 7.12 divided by 0.0323. And I'm getting 220 1 over seconds or hertz. And I could find the period if I wanted to by taking the inverse of that. So the other thing that we're going to kind of first talk about are transverse waves and that speed of a transverse wave. So a transverse wave, once again, is like a string, so that's vibrating. And just think about a guitar. There's different strings. They have different thicknesses, so that means they have different masses. And to tune them, you adjust how taut they are, how much tension are in them. So the speed of the wave has something to do with the tension. So this is tension, not period. So you could even call this FT if you wanted to, if that was confusing to you. Divided by the mass per unit length. So depending, it's kind of like the mass density of the material. So and we call it mu, and if I want to know it, so for example, if the string is 1 meter long and it has a mass of 1 kilogram, it would be 1 kilogram divided by 1 meter. So everything needs to be in kilograms and meters. So if we wanted to know the speed on a guitar string that has a mass of 0.300 grams, so a mass of 300 grams, we need to know what that is in kilograms. Well, there's 1,000 grams in 1 kilogram. This is another example of knowing how to do your conversions. So it'd be 0.300 kilograms. And it has a tension of 10 newtons. And it has a length of 1 meter. So my speed of propagation would be 10 newtons divided by mu, which is your mass per unit length, or 0.300 kilograms per 1 meter, which is 0.300 kilograms per meter. So if I take 10 and divide it by 0.3, and now I need to take the square root of that, it's going to be equal to 5.77 meters per second. So the wave would be traveling at that speed up and down the string. So the other thing that we can talk about is we can talk about superposition of waves. So whether it's a transverse wave or a sound wave, when waves meet, they interfere with each other and they produce a new wave. And it's really the algebraic sum of those two waves. So remember we talked about simple harmonic motion. You could model the position of the wave as a function, a cosine function. Well, sound waves and waves, transverse waves on strings can be modeled using sine and cosine functions as well. And if you had one wave with a certain sine function and another wave with a cosine function and they meet each other, they will produce a new wave that is the algebraic sum of the amplitudes of those. So for example, if we take a look at wave 1 here in this first in constructive interference, if you look at wave 1 and wave 2, they look exactly the same. They have the same frequency, the same wavelength, and everything. So when I add up their amplitudes, this amplitude plus this amplitude is equal to twice the amplitude. So if this is the amplitude of 1 and this has the amplitude of 1, then this has the amplitude of 2. And then if I do that for every point, I can construct a new wave. And how do I hear that? Well, it sounds like the identical sound, but it is a louder wave, right? The more amplitude, the louder. I can also have destructive interference, right? I could have a wave that looks like the inverse of another wave. So when this has a -1 amplitude and this one has a positive amplitude, the amplitude here is 0, and it's actually canceled out. So when you have a new wave form that has less amplitude than either of the original waves, it's called destructive interference. And this is exactly what's happening when you use noise canceling headphones. There is a sound that is being produced in the headphones that has an amplitude in the exact opposite direction of just general noise. You can never get 100% cancellation because noise is very complicated, but you can probably buy some really expensive ones that cancel out 90% of those sound waves.